Hi students, welcome to Year 11 Earth and Environmental Science. This is Module 1, Earth's Resources, and video number 7 and we're going to be focusing on density, and specifically density in relation to the different layers in the Earth. So in this particular video, we're just going to introduce this idea of density and the calculations associated with density in order that we can conduct a practical investigation in class. And what you need to do is to look at some different samples of rocks and potentially minerals to get a bit of a sense of the differences that can occur in density between each of these. And we haven't had a look at the center of the Earth, but we've made some conclusions about what the internal structure looks like based on some of the observations that we've made, particularly in relation to seismic waves and how fast they travel, or at least how the speed can change as they move from one medium into another. And the key difference in the different media is this idea of density, how tightly packed the particles are together, and also whether or not that represents a solid or a liquid. So what we'll be doing is looking at some different samples of rock, measuring the densities and seeing if we can see some differences, and then making some conclusions about whereabouts those particular samples could be sourced. So your success criteria is pretty straightforward here. You just need to be able to measure the density of different substances. Of course, the problem with rocks is that they don't always come in beautiful, consistent, regular shapes. They're often very irregular, and as a result, you can't just calculate volume based on the volume of a cube or of a rectangular prism or a sphere. We have to make some slight adjustments when we're trying to work out our calculations for density. What we want to do, of course, is then relate the differences in density that we see for different rocks, assuming we find some, to differences in density in the different layers of the Earth, and see if we can link these together and potentially propose reasons why there might be differences. So what we want to have a look at then is this concept of density. And density is how tightly packed the particles are in a particular substance. So it's all about mass, the amount of matter, and volume, the amount of space. So we're looking at matter and we're looking at space. And obviously the greater the space between the matter, the lower the density, and the less space there is between the matter, the higher the density. Now also, if the individual particles of matter are heavier, have more mass, then that will also affect this value for density. This is the Greek letter rho, and it's often used to represent density, and we can calculate this value of density by dividing the mass of any object by its volume in order to calculate the density. Obviously, this is a nice easy one for solids, especially if they're regular solids, as I mentioned before, like a cube or a sphere. If they're irregular, they have bumpy edges and we can't easily calculate that, then we have to find a different method to do that. Usually, depending on the size and the type of material, we're measuring density in kilograms per cubic meter, or in the laboratory, most of what we will be doing is using this unit of grams per cubic centimeter. And of course, a cubic centimeter is equal to a milliliter, and that's one of the measures that we do look at when we're looking at displacing particularly things like water. One important thing is that the density of water is 1,000 kilograms per cubic meter, which is the same as 1 gram per cubic centimeter, or as I mentioned, 1 gram per mil. And that's an important thing to remember, and something that we'll be having a look at both in terms of the types of materials that may either float or sink in water, but also in terms of displacement. So we often get ranges. The values do vary from source to source. So one of the important things when you're looking at density is not to get too caught up in absolute values, but to try and get an understanding of a trend that you can see. And hopefully the most obvious trend that you can see here is as we go deeper into the internal structure of the Earth, so as we go down into the Earth, the density increases. And we've said that that's partly because of that transition from planetesimal to planet, when the heat that was generated and the flow of the material allowed different substances to settle at different rates, and therefore the most dense materials sank to the center of our planet and the least dense materials can be found closer to the surface. And so you see that in the patterning as we look down. We just kind of get a bit of an overview of what's happening. You get this general trend as it goes down. Now we know that there's some places where it jumps quite considerably, these places of discontinuity, where we see not just a general increase in trend, but a massive increase or sometimes a decrease, which is telling us something about a boundary between one layer and the next. So this is what we're setting as our context for our look at the density of different types of rocks. So what specifically are we going to be doing to look at density in a little more detail? Well, this is what we're going to be doing. We're going to be examining some different samples of rocks from what we can conclude to be different parts of the Earth. Now, that may not be the case. They may just be representative of the types of materials that we find. But what we need, if we're going to measure density, is we need mass and we need volume. Now, mass is probably the easiest one because we can just stick it on an electronic balance and we can record our reading for mass. Volume's a little trickier. As I said, because most of the material that we're looking at is an irregular shape, we can't use a straight formula to do that calculation. So instead, we're going to use Archimedes' displacement method. And what Archimedes says is if you place a body in a certain fluid, like water, then it will displace an amount, that is, the level will move up, and the amount that it displaces is an amount equal to its volume. So therefore, in the one to the side here, if the difference between each of these two, if the volume that's been displaced is equal to 10 mils or 10 cubic centimeters, then that is what we would conclude to be the volume of that particular object. We're also going to carry this out with the Eureka cans. And we'll make some conclusions about the accuracy and the efficacy of using these sorts of things after we've had a go at this experiment. So that's what it's about. Have a look at a few different types of rocks and minerals, draw up a table to make a list of the mass, the volume, and hence the density of each of these, and see if you can source these back to the part of the Earth that they may represent. Thanks for watching.